An electrolytic cell contains a reaction that's not spontaneous, which means really that it starts with, in the spontaneous reaction, what would be the products. So an electrolytic cell has a non-spontaneous reaction. That is made to be spontaneous. So that means either connecting it to a power supply or to a battery that will make the reaction proceed in that non-spontaneous direction. Let's look at a relationship, though, between moles of electrons or charge and electrons. And there's two different expressions for charge. I'll just call it charge. All right, so let's do that up here. And we want to dissolve the copper. Well, we can dissolve that by passing electricity through here from a power supply. Okay, so let's say this is a power supply and it has two electrodes here. If we want to dissolve the copper, we want then that copper in here, let's say, to become a copper 2+. So what we would do is we'd hook something to here that would pull electrons off the copper. So we would hook this to the positive terminal of this power supply with a wire. And then we'd have a negative terminal connected in the solution that would be connected to some other electrode that we'd have in here. Doesn't really matter what it is, but that would be like where the electrons would be deposited. Because the solution has to stay neutral. And that creates a circuit because the electrons will be, is that the right way to do it? So this would represent a half reaction where copper solid loses its electrons, become a copper 2+ in aqueous solution, and then provides the 2 electrons to wherever it's going. That's all we need is a half reaction when we look at these electrolysis, when we look at the stoichiometry of electrolysis, because that gives us the ratio between the electrons and the copper that in this, whatever it is, it's going to be undergoing either oxidation or reduction. So there's a certain amount of charge that flows through the wire when this occurs. You have electrons flowing through the wire this way, and there's going to be a charge on those electrons. That flows through the wire. So the more electrons that flow through the wire, the more charge flows through the wire. Well, that amount of charge is going to be equal to the current that flows through times the time it takes. Okay, current times time. Current is in units of amps, and time is going to be in units of seconds. So amps times time is equal to charge. Charge is in coulombs. So amps has units of coulombs per second, where C is coulombs. Okay, so that's one relationship. We could kind of make that a little smaller by saying that current charge is equal to amps times T, A times T, amps times time. Now, that's also related to how many moles of electrons pass through there. So charge is also equal to the number of moles of electrons times the charge on a mole of electrons. So that's N times this constant, F, Faraday's constant. So N here is moles of electrons. F is 96,485 coulombs per mole of electrons. This N is going to, will end up being this value if we were doing stoichiometry. Whatever value we solve for the moles of electrons will be over there. And then we'll also, that's going to be related to the moles of copper that dissolves. So these two things, if we put them together, we get a formula that says that NF equals amps times time. Okay, that's a very helpful relationship to have. So let's look at an example using this copper here. I'll write that formula down again. So we could say, we could try to answer the question, following question. How many grams of copper will dissolve if the circuit is run with, let's say we have 0.25 amps for 32 seconds. Okay, so we have amps and time, and we want to calculate grams. So basically what we're trying to do is get this in grams. And just like any other stoichiometry, if we have some amount to start with, we can calculate that. And we don't directly have the amount, but we have enough here to calculate this in moles of electrons. And that would be the N, because we just said that we're going to use NF equals amps times time. And we're going to first calculate N. So N would be equal to amps times time over F, which is 0.25 amps, or coulombs per second, times 32 seconds, divided by 96,485. And that's coulombs per mole. Okay. So let's see what that is. Pretty small number. So that would be 8.3 times 10 to the minus 5 moles. I guess I should have a larger amp. Yeah. Okay, so that's what would be here. So to calculate grams, we just use now the mole relationship between these two, and then multiply by the molar mass of copper. Make a little bit more room here to do that. We use the mole ratio. There's 1 mole of copper and every 2 moles of electrons, and then multiply that by mass. Periodic table. So copper is 63.55. Grams per mole of electrons. That's our answer. So that's 2.6 times 10 to the minus 3 grams And we could express that also in milligrams if you want. So that's 2.6 milligrams of copper that would be dissolved. So that's one example where starting from a current in time, we're calculating an amount of reactant in this case. The other central problem like this is if you're starting with an amount, so if we start with the amount of copper, we could also calculate how long it would take to dissolve that amount. In other words, how many seconds by going backwards. So we would start with this number, we calculate the moles, and we plug that moles into NF equals amps times time, and we solve for time and that kind of a problem. But I'm not going to do that whole thing right now. There's examples of both of these types of calculations that I'll